Let's get started. Well, we have an enthusiastic bunch of you here, which is good. But so I'm not going to be here for long. I have meetings after 1 p.m. But I can answer your questions related to the final until 1. After that, I think Kevin and Rachada will take over and go through any questions that you want to go over in the past exams. And that's actually a good way of actually studying, right? Let's start first quickly. First, I think that's important. I don't think we ever did this, right, for the lab 6. Oh, I should have animated this. A lot of people did extra credit for lab 6, which is actually great. And Kais, Ragav, I guess not many of you are here. Kais is here. Sohil. I thought I saw him, right?
Yeah, he may have went outside and got pizza.
No, okay. Akshay. Jared, who's not here. Pete. Amanda. And Ashish. There you go. Your name is up there. So. So but you guys knew that you got extra credit. It's actually 1, 2, 3, 4, 5, 6, 7, 8. If you think about it, it's about 30% of the class, which is nice. Well, congratulations. I enjoyed reading some the reports here, even though you may not have gotten it correctly. That's okay. What matters is really you tried and you actually tried to get it to work correctly. And actually, I think you got it correctly, but some numbers didn't match up in some cases. But that happens. It was only a very little time. Yeah. Any questions? There's Lab 7 extra credit we haven't graded yet. I mean, you got your Lab 7 grades if you submitted early. If you want to resubmit, please resubmit. So Lab 7 is still being accepted until tonight, right? 11:59 p.m. Yeah. So there will be extra credit for Lab 7 too. Now you guys are working hard, which is good, but hopefully you're learning a lot, which was the biggest intent of this course actually. So course evaluations, I'd like to give you some reminders. Course evaluations, your name was up here too. You missed it. Yeah. Line for the course is too long?
Oh, no.
Yeah. You got some extra credit too, but you knew that. That's good.
All right.
Okay, I'd like you guys to do the course evaluations. Please do them, and we discussed this last time. It's important. I read these carefully. We try to improve the course. And remember, there's always conflicting feedback, like what we've discussed last time. Some people want single-person assignments. Some people really hate that. They want multiple-person assignments. And maybe in the next incarnation of the course, we'll have heterogeneity. That sounds like a good idea, actually. I don't know why we didn't think of that idea before, but that's how the feedback actually gets incorporated. Okay? Please take the time to write the feedback. State the things you liked, and I hope you liked a lot of stuff in the course. You learned a lot of stuff. You learned about Bloom filters, for example, hopefully. That's good, right? And topics you enjoyed, and what do you think the course contributed to you. And we've already discussed this. Don't just say the courses. Hard and fast-paced because you knew that, right, coming into it. And hard things are good sometimes. Okay, and there's this. So this is a collaborative project of this course. So if 25 of you or more fill out the evaluations, everyone gets 0.25% extra credit. Not that you're here for the extra credit or grades, but it doesn't hurt, right? Okay. And there's another opportunity for extra credit still, which is the multi-core cache coherence lab, right? How many of you are planning to attempt this, just to get a... Well, that's pretty cool, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No.
We attempt it and say it's not quite correct. Do we get totally squat? Like, do we get nothing for all that effort?
Well, it is possible. We'll go over your code and look at what you've done.
Okay.
So you will get some partial credit. You may not get 100%,
Right.
or maybe 50%.
Like,
Absolutely. I mean, yeah, you will get credit for the attempt. But if your attempt is just submitting the starting Lab 7 code, that won't work. It depends on the level of the attempt, certainly, right? You'll get benefits proportional to the level of attempt.
And the submission date can't be extended beyond?
No, we're not going to accept any late submissions. I mean, this is not even a deadline, right? This is really extra credit in the true sense of the term. I mean, everything else has been extra credit too, but this is actually something that we are doing extra to help you out also, right? You can think of it that way too. But you can submit afterwards, but it's not guaranteed to be graded. We need to turn in the grades, right? But don't count on it, basically. Okay? But it will definitely be fun. I guarantee you that. That's MESI Cache Coherence Protocol. You'll learn a lot from it. And when you go out into industry, you will see that you have learned a lot from it, maybe. Even if you don't believe me right now, you will see that. When you actually have to deal with this coherence thing that you should have implemented when you took 447, right? And it doesn't actually, this is not only in processor design, right? Coherence is a big issue in distributed system design. Even if you go and do distributed systems programming, you'll have to deal with stuff like this. How many of you had Gmail open in 3 different windows and you see a huge inconsistency? No one? Yeah? You did? Yeah. Like, you actually see some emails in one window, you don't see some of those emails, you delete one from here, it doesn't appear over there. That's a coherence problem, right? It's actually the coherence problem in the distributed system. Why it might happen? Because it might happen because of network delays. It might happen because some of it is running out of this data center versus that data center, right? It can be getting copies from, it can be getting served from different copies of the Gmail server. It's a coherence problem. When do these updates get pushed into all of those other servers, right? No. And how do you actually find the most up-to-date data if updates don't get pushed to all of the servers, right? And there are other things that are involved also, right? Because there are requests that they need to load balance across these data centers. But it's essentially the same problem. I mean, the fundamentals of it is really coherence. And this is one way of dealing with it. Now, if you want to adapt this to a distributed system, maybe that's not the best protocol, right? But I'll let you think about that. And you may actually be thinking about it in a few years, or maybe next year, or maybe during your summer internship. Okay, so we're here for the final exam. You already know that this is next Tuesday, right? Tuesday, yeah, May 5th, evening, 3 hours. That's the location. Don't go to where you're used to going, CIC, 4th floor. It's not there. It's at Baker Hall, A51. It's comprehensive. 3 cheat sheets are allowed. And I guess this is an old slide. I had a slide level coherence. Okay. Okay, I think we've covered that. Basically, I have the same advice as before for midterms 1 and 2. Study hard, look at the old solutions, look at the old exams, try to solve them. Look at the exams, past exams where there were questions that you didn't get. They may appear in some form in the final. And we're going to, actually, let me, this is still from the last one. Do you guys want to still talk about grades, or do you want to move to the review session? Any questions? I'll just ask that. Yeah? Yeah? No questions? Okay. I think I'm actually really happy with all of you bunch. You guys are really good to interact with. So you'll all do well, I think. But don't drop the exam or anything. Just do it for learning, okay? Say it again? Okay. Okay, we already talked about this. So I think basically what is the exam about? It's about all of this thing. So I finally covered all of them, so I don't have any blue over here. So this is the second half of the lecture schedule, which is the memory hierarchy and multiprocessors. And this is the first half, which is fundamentals, ISA, and single core design and execution models. Right? And you can expect questions on any of these. Yes?
Sorry, I did have a question for you. Those of us who, or at least for me, I got waitlisted because it wasn't open to undergraduates.
Oh, really?
Yeah.
Oh, really?
I was in the course, and then they emailed me telling me that they had put me on the wait list.
Okay.
So
I'll check with them, but you should not get waitlisted, or you can email me,
okay,
and I'll put you on the course. Because if you're taking 447, you should really be able to take the course without getting waitlisted.
Sort of like policy where because 740 is a graduate level class, that all undergraduates like automatically
Yeah,
go on
so
the wait list
the-
until you say that we can move on or something?
yeah.
So that could be that actually. Why don't you email me and I'll get you individually on the waitlist? Maybe there's some test over there that checks whether you're an undergraduate,
Right.
and it doesn't do the matching for the course because it's a graduate course. But if you want to take it, and if you're waitlisted, just email me. That shouldn't be a problem at all. I mean, we've had actually 740. 740, 1/3 of the class is usually undergraduates, and there are a lot of good research projects that came out of it in the past. Remember, this is a project-oriented course. Once you have 447, you're at a very good point to actually do the next steps. So you can actually, maybe you already have some ideas, maybe you don't, that's okay. But you can do a project that can affect the way things are implemented. I can go over the projects, but let's talk about the final review session. Any other questions related to this? Okay. Okay, this is basically what the lecture exam will be about. Hopefully you know all of these grayed out things. Okay, I have about 10 minutes, 15 minutes or so. Any questions? Otherwise, I can leave the floor to Kevin and Rachada, who can go over some of the exam questions which they have over here. That's the midterm exam too. So you can ask about any of the questions. And the solutions are relatively detailed online as well. And I'd actually also recommend that you study past exams too. That's always a good thing. Some of them are in your homework anyway. But. Any questions for me? No? Feel free. Or do you want to ask questions about the exam homework? Anything I should clarify? No? Everyone? Oh, yeah, go ahead.
Is the final exam the same length as our midterm, or does it have extra questions?
So, I mean, it will be maybe roughly the same.
Okay.
But there may be bonus questions. Let me put it that way.
Okay.
Yeah, and bonus questions are good, right? You get extra credit. It depends on how hard they are, right? Yeah. Anything else? Any concepts that you don't understand? Everything is good? You all know about GPUs? Or other execution models? Out of order execution? Branch prediction? Those are good topics, right? You can all do renaming. Yeah.
I always seem to struggle with the difference between vector and array processors.
Mm-hmm.
So is it like a good way to remember how to differentiate?
So if you, it's very simple actually. The good way to remember is vector processors. You have a vector. You operate on each element in consecutive cycles in a vector processor. In an array processor, you operate on each element concurrently at the same time. That's the only difference actually. Make sense?
Yeah. Right.
Yeah. So you can think about a vector processor as pipelined, whereas an array processor has having many functional units that can do the same thing. Okay? But existing GPUs are both vector and array processors in a sense because they have multiple functional units that can do the same thing, as well as they have pipelining. So if you remember that picture that I had from the SIMD lecture, you could actually do things horizontally across different functional units and also vertically in time. That's the time-space duality. Maybe I should leave it to Kevin then. Yeah. It was really fun to teach this class, actually. I really enjoyed it. You guys all have really good attitude and energy. And feel free to stop by and chat with me anytime. First, you should send me email to figure out I'm in town or not, but I'd love to chat with you about anything. It doesn't have to be computer architecture. If you want to take 740, if you don't want to take 740, that's okay. If you want to talk about research, jobs, internships, about anything, feel free to come by, stop by. I tend to be busy, but don't let that scare you. That's not it. If you don't send me email, that I don't know that if you want to talk with me, right? That's impossible for me to somehow magically read. Although you could have a good predictor maybe, but that's you can try that. So feel free to stop by anytime. It was really fun having you guys in class. Okay, now it's Kevin's turn, I guess. Do you have questions prepared, or You'll just take.
I think we're just gonna go over midterm 2 first.
Oh, okay, that sounds great.
Maybe we can go over midterm 1 or
Mhm.
some other questions.
Cool. That's a really good plan. 2 will not come up. But the virtual memory question will come up. Oh, I don't know what similar flavor means. You will need to be able to figure out the page size right now. Is that a good enough hint? So know your virtual memory and its interaction with caches and stuff. That's such a core part of the system. All right.
See you later.
Yeah, see you. Yeah.
Do you
That's
want?
mine. I'll take it and I'll give this to Archie. You might want to wear that. So that
Okay.
See you guys.
So like I said, we're just gonna quickly go over midterm 2 and answer your questions regarding the solutions. And I think afterward, if you guys have some more questions about midterm 1, we can go back to it. But now let's just quickly go over it. So I think for the potpourri part, it should be relatively straightforward. Do you guys have any particular questions on the potpourri part?
The D part?
D? This part? Okay. So basically, I think Professor Mutlu explained it before that some of you probably caught something weird about this being from shared to exclusive state. So usually when you have a write in a messy protocol, you would go to basically a modified state, right? So in this case, it's a tricky question. You will need to, so your cache controller will need to handle extra actions when you actually want to go from shared to exclusive. So I think that's where the tricky part comes from. But the answer makes sense, right? You will need to invalidate all the other cache lines and basically write back.
Move from shared to exclusive at all.
So it's like it's a protocol that we design or computer architecture design, right? So there's no one golden protocol. There are always trade-offs. So this is one protocol that we thought of, but it may not be the best idea. Yeah. But we just want to test your concept of understanding between transitioning different states in the messy protocol. Yeah.
Why you have to flush? I got that you get to why you have to validate, but then why you have to flush as well?
So this.
The solution said that you should validate it as a fact.
Right.
So what did you write back and why?
So write back data from other caches, other private caches.
But if it's shared, right, and then you want to go from it being the only shared copy to the only copy, why is it not sufficient to just say all the other copies in the cache are useless, or like invalid? So I'm confused why you have to go back.
Right. Actually, now I kind of see a point. You're saying that in shared state, all the cache lines should be completely clean. Right.
But it's on a processor write, so this copy becomes invalid. And so if you wanted to, so it becomes modified on a processor write. So if you wanted to transition to exclusive instead, you need to flush.
Oh, okay.
Is that a question of path? Is you go from shared to modified to exclusive? Like, so directly from shared to exclusive should just require the validation.
Yeah, so I think we don't give you a complete diagram here, but I see your point. If I assume that when I'm in modified state, assuming that dirty copies can happen in 2 states now, basically exclusive and modified in this case.
Yeah.
This is what we're assuming. Modifying exclusive.
I think that with exclusive it has to be clean.
No, I understand. That's a messy protocol. But in this question, what we're saying is we're going to make the copy dirty in the exclusive state as well. This is why, like, 'cause some of you answer the questions.
Okay, so that's why the solution has flush, because then it isn't dirty anymore, even after a processor write.
Right,
So
so-
to be correct, you have to say only invalidate and modify exclusive to also mean a dirty copy.
Yeah, so basically, okay, so you guys understand that. I think all of you understand that for a messy protocol, what you want to do is on a modified and shared state, you want to go to you want to go from shared to modified, right? Right, that's a messy protocol. But here, we're tweaking it. We're tweaking such that you actually go to exclusive. But in the typical messy protocol that we learn in class, exclusive is supposed to be clean. But in this question, that's not what we're assuming. We're tweaking the messy protocol such that exclusive state is actually dirty. So we tweak the protocol. Yeah.
I don't think that's how you're tweaking it. That's why you need to flush, because then after you write, then it is still clean. If you write and then flush, then the copy is now clean, and so you can
Write
be in
and
the exclusive
flush.
state. Flush is into the lower level cache. So even though you're in the exclusive state and you've written, the copy is still clean.
He's saying
I
that
don't-
half from shared to exclusive has to be shared and modified to exclusive in case of processor edge. So it has to be flushed through shared. Otherwise, half it doesn't make sense. You can't go from shared to exclusive. You wouldn't go from shared to exclusive for a processor, right?
I mean, Kevin,
Yeah, go ahead.
what you're saying is that the exclusive state, in this problem, if we're assuming that the exclusive state can have dirty data, then you wouldn't have to flush, right? Because then you could just validate.
Right.
But in the answers, it says you have to flush. That would imply that exclusive
It's clean.
is clean.
Right. So I guess. Yeah. So what I said could be wrong. It seems like. Yeah. Okay. Yeah. But I think the point to keep in mind here is when you modify, you want to go to modified state. You don't want to go to exclusive state directly. Yeah. So, okay. So I guess everything is clarified now.
Yeah,
I guess I was confused myself as well. Yeah. Sorry about that. Yeah. Okay. So let's see. Okay. So this part is memory scheduling, and I think I'll just quickly go over the answer for part A. I think most of you got the answers already. So we give you some mappings from physical addresses to the DRAM addresses, or which particular components in DRAM. So for part A, we give you some of the informations, such as row buffer hit rate and the list of requests that we want to schedule. So the first thing to note here is the row buffer hit rate is 1/3, meaning that two out of these 6 requests are row hits. Can you guys see it? Yes. Right. Okay. So one assumption we made in this question to begin with is all the rows are closed. That means we'll schedule A first using FRCFS. Okay. So basically A will come first. The next we'll schedule row buffer hits going to the same row as A. So from this question, we already know a piece of information, which is the cache line size, 64 bytes. That means the cache line offset is 6 bits. Right? So we can search through all these requests, find those that match with, that have same bits in the upper columns, banks, and row bits. So if we scan through here, we can see that D must be a row buffer hit. Right? Okay. So we know that D is a row buffer hit because all these upper bits match with A, and the bottom 6 bits in this case is 1 0 0 0 0 0. So it's in a different cache line, but same row and same banks, and I guess same channel. We assume a single channel here. So now we know A, D go to the same row, and D is a row buffer hit. Row buffer hit. But we need to find another row buffer hit in this question because there are two of them. So the second one is actually, we have a couple candidates. So the closest one you can probably find is either B or E. But if you look closely, E is actually the best candidate. You have to basically write out the bits, the hex in bits. So for in E, if you write out 8 and the bottom okay, so basically if in this case we make E the best candidate, and which will be our second row hit, that means B cannot be a row hit. It will be a row miss. So if you look at the bit pattern difference between B and E, it's only 1 bit shifting left. So B only has, it's the same as E except it's shifted left by 1. Do you guys see that? So this is B and this is E. Okay, so given that we know that E is also row, based on this, we know that E here is a row hit. So that means the bottom 12 bits belong to both the columns and the cache line offset. And 6 of them belongs to the caches. And the other 6 bits belong to the columns. So in total, basically we have 12 bits for our basic row size. So basically here, the row size is 4 kilobytes. Okay, so I think this is relatively straightforward, right? Okay. So part B, let's take a look. Okay. So in part B, we'll reuse the information from part A, where we already decoded the row address, not the row address, the row size. So we know the only column address bits. And so in this question, we gave you several information, a row buffer hit latency, row buffer miss latency. And we also tell you that all the row buffers are closed at time 0 as well. And again, we assume FRCFS scheduling policy. So in this case, A will start first again. And the other piece of information we have is it takes 320 cycles to finish all the request here. So given the information on row buffer hit and row buffer miss and latency of each request, we know that 320 is broken down into row buffer miss plus its request latency and 1 row buffer hit plus its request latency. Right, so this adds up to 320 cycles. Okay. So basically, now what we need to find is we need to find 1 row buffer miss and 1 row buffer hit. So we already start with A, so we can see if we can find row buffer hit going with A. All right. So in this case, given that in part A we found out the bottom 12 bits are for column addresses and cache line addresses, we can find an address that have a top, I guess in 32, so basically top 20 bits that are the same. So in this case will be D. So D will be, you can see the pattern matches exactly with A with its 20 bit, top 20 bits. Okay, so A and D go into the same row. And B and C, in this case, they have to go to different rows. Sorry, not different rows, different banks. Because if they go to the same bank, they will cause cache conflicts, row buffer conflicts, and that will actually incur more than 320 cycles. So we know that B and C must go to different banks. Okay. So again, now what we do is we examine the bit patterns across these requests. So let's list them out. So for B and CD, let's look at, so its hex is 1040, so 001, and let's ignore the rest. And for C is 3040. Okay, so we know that all these bottom 12 bits, they don't really matter at this point because they belong to the cache line and the columns. So we really need to take a look at these bits, 1, 3, and 4. So now we need to find out the number of minimum banks. Let's start with assuming the bank bits, in this case, let's start with, let's say, 1 bit. So if it's only 1 bit, if we look at here, that would mean B and C will go to the same bank, so which is wrong. So it cannot be 1 bit. So if we shift left by 1 more bit, we can see that B will go to bank 1, C will go to bank 3, D will go to bank 0. So which is a good answer? So this is the minimum number of banks we have, where this is the minimum number of bits we can use to encode number of banks. So in this case, we are using at least 2 bits to encode number of banks. So the answer would be 4 banks. Okay, I think several of you sort of stop at the top, just assuming you have 3 banks, but you really need to go down to actually examine the bit patterns to find the bit encodings for the banks. But we did give you partial credits for putting down 3 banks as an answer. Okay? And I think Rachada will go over the messy protocol with you guys.
Okay.
In the microphone? Push it.
Okay. All right. So, are there any high-level questions about this particular problem? Otherwise, I'm just gonna go through the other steps. Most of the yeah.
Is there a different result if you assumed that you went from shared to invalid, or from exclusive to invalid or shared?
Wait, from exclusive.
Because you can go from exclusive to invalid or shared, right? Or sorry,
from shared.
modified.
From modified.
Yeah.
Right.
Modified.
So it depends on whether you have a read or write.
Okay, yeah. But the question is, do you go from modified to shared or modified to invalid? Because you can go from modified to invalid, and then the left is, that's an option.
Yeah. So that's also an option. Yeah. So we follow the messy protocol from the lecture notes, but not from the lab. Because you look at the lab, the only difference from the lecture note and the lab is if you are in the shared state and you have a write to another line, you go to exclusive. which in that case you have to make sure you invalidate. You write it back afterward. Any dirty lines. Yeah. Right. So I guess how to approach this problem, you can just go over each of these instructions line by line, and the only tricky part here is at the third and the fifth instruction here, because it first store to that address and then you load from the same address. So let me go over the address 110000 C0 first. That's load to P1. So if you look at the block size and the size of the cache, you realize that 110000 C0 will map to the fourth set of cache, well, whatever cache it is. So this would be cache number 1, which is this P1. Okay, so this particular set, right? And the final state, as you've seen here, is exclusive. So one thing you can assume first is, if you have a load to that line, one of the possibilities is that set might actually have other address. So the first thing you fill in here is you don't really know what the tags are, because it's possible that it might be just exclusive and you have a load to itself, or it might be actually other address. And if it's other address, you don't really know what are the messy state either. So this should be, you don't know here, so it's MESI. Anything is possible. After you have that load, you write back the data if it's invalidated. If it's in other state, if it's exclusive or share, you load the new data to that set, and that becomes exclusive. What happened?
I didn't notice that we have to answer exit to tag values.
Oh, okay. So actually, if you have that errors, I think there are 2 more people, because Xiaofan talked to Onur about that particular error, come to me, so I can regrade this particular question. I think you might have that. So you guys should come to me with your exam so I can correct it and remark it. I think there's one other person who's not here, so I guess I posted on Piazza about it. But yeah, you guys now know, so you guys should drop by. And the next thing we have to deal with, and we have to be careful with this part, is, are there any eviction? Are there anything that happened to that particular address on the other cache, on the other processor? So if you look on this particular address 1100C0, which is the fourth set of anything that have the tag 110000, you see that processor 0 have it, and it's invalidated. Also, what else? Let's see. And that's it. So you know that this line 0x110000 has to be there, because there's nothing that you don't have a load or store to that processor. The address is supposed to be the same before you get to that state, right? And if it's a load and this becomes exclusive, you have to be aware that it's the sole owner of that line, and this set is already invalidated. So originally, before that happened, it's invalidated. So in here, you write in invalidate. The next instruction, store to 110080, that's set 2 on processor 1 again. So if you look at this diagram, the only difference here is you have modified state here instead of exclusive. But so if you see here, similar scenario happen, you don't really know what you're writing into, so it might be other address. So in here you write X, and this can be MESI, can be anything. And now because this is stored and modified, and you have this particular address being invalidated. And because it's a store, it's a write to that address, you don't really know what the states are at the beginning of that address in process 0. The reason because why that happened, because if it's a shared state, or if a modified state, or if it's an exclusive state, you have to write back, right? When you have a store from the other processor coming in. So when that happens, you have to invalidate that line. So the key here is when you realize that the address here is the same. However, you don't know what the Macy state earlier is, because that store instruction R2 will cause the invalidation. So that should become unknown. So it should be Macy. Now let's go to the fourth instruction because it doesn't deal with the combination of store and load. So it's one FFFF00, which is mapped to the set 0 of P1, which is cache 1. Again, you can assume that, well, I mean, it's with a similar logic that I described earlier. The tag is unknown, and this is Macy. And let's see what are the effects of this load to other cache blocks. So if you look at these final state, you see that there's also the same tag over here on cache 0, and the Macy state is a share. Right, so you can put it in here. One F. Miss one F. But because it's a share, there's no load and store to that particular address, so you know that the tags have to be the same. If you think about the state, there's one state that's impossible to be. They are impossible to be in, which is invalidated. Because if there's a load to that block, and this is already invalidated, that should become invalidated, but it's share, which means that it's either already in a share state. It can be in a modified or exclusive vessel, because if there are those two states, what happens is when you have a load to the other processor, you update the state saying I'm share. If it's modified, you write the data back, and then you load the actually correct data to cache 1, which caused the load. If it's in exclusive, you don't actually have to write back anything. You update your state to the share state. So the three possible states is MES. And lastly, let's go over the one FFFFF40, which happened twice. The first one is the store. The second one is the load. There are three tags, three processors that have that tags over here, which is cache 0, cache 1, and cache 2. And the last thing that happened is a load to processor 2. So you can, when you look at this, you can put in X over here and MESI. Because ultimately, you don't really know what's originally in there. It might be the same tag. It might be that same data. It might be some other address, but got evicted from that particular load. Similarly, let's go to P0. So you can also write X and MESI over here. And the last problem we have to figure out is what happened to this particular invalidation here. If you look at the tag and you see that even though there's no load or store to that processor on that address, but you have that tag in the cache, so you can assume that set 1 of cache 1 will have the same tag at the beginning of F. And that's a store to R3 on P0 over here, right? And the load that comes afterward causes it to become shared for cache 0 and cache 2, but cache 1 is invalidated. So one scenario that can happen is it's already been invalidated before you execute those 5 memory instructions. So invalidate is possible. But because there's a store to R3, and that store might have caused cache 1 to invalidate its own cache data, which means that even whatever states they are in before, it has to become invalidate. So modify, exclusive, and share are also possible. So that's all. The rest, they retain the tag, the same tag and the same messy state, so you can always put the rest in using the old data. So it's 0x10f. And this thing would be the same. And that's how you solve this question. Yep. Then the next question is AMDAL. Do you want me to go over that? I mean, yeah.
I don't think we'll go over everything, so you can ping on that. Sure.
But that one is a long one.
Yeah. Okay, so I guess let's not go through all the answers here, but do you have any questions regarding Amdahl's law? So I think this question is pretty straightforward. Yeah, okay. And I think part C, we actually have the equation on one of the slides, in case you haven't noticed. But if you happen to jot down on your cheat sheet, you should probably got in this question. Okay, so I guess we'll skip it now. Oh, good. How about 5, prefetching? Is there any part we should go over? Yeah.
Or actually, are you guys having office hours on Mondays? On this Monday?
Monday. Sure, why not? Okay. Any question about prefetching? G. What's G? I see. So this is actually a trick question. So one thing to realize here is we increase the cache size to 32 kilobytes. So what does that mean? That means all 4 unique blocks, they'll fit into the cache after the first iteration. Right? Do you see that? Because there are only 4 unique blocks here, not 5. There's A plus 3, A plus 6, and A plus 5. So they'll all fit in the cache. And the problem with prefetcher is that unless you have 100% accuracy, you will somehow waste bandwidth because you are sending extra requests to fetch extra cache blocks, and they can cause pollutions, or those requests they just sort of cause wasted bandwidth on the bus or in the memories itself. So that's why this question will be there's really no prefetcher that can beat the baseline as long as it can keep accessing those cache lines in the cache. Got it? Okay. Yeah. I think some of you were kind of confused by this question and left it blank. So I assume you probably realize everything fits in the cache. Someone shaking head.
Yeah, that happened to me. I was sitting there going like, what do you mean like smaller memory bandwidth than the baseline because you don't need prefetcher? I was like sitting there for 2 minutes going, no, it's right here.
Yeah.
I think my answer was like, don't prefetch unless you get more misses. So it won't prefetch.
That's a tricky question. So just be aware of these sort of questions. Just believe in yourself. Okay, so I think 6, it's pretty straightforward with all the equations and the solutions. So is there any particular part that we should go over in 6? Yeah.
Just go over B. I know it's probably simple, but I understand how to do it.
B, this part?
Yeah.
Okay, so I think one thing to realize here is let's see. Okay. So here we give you a configuration, a channel with 2 ranks, right? So that's actually very important for part B. Because on a single channel, so here assuming this line is a single channel, okay? And I'm drawing 2 ranks. So this is my ugly rank 1 and rank 2. So basically for rank 1 and rank 2, they will share the same bus on a single channel. Does that make sense? Okay. So in order to determine command bus utilization shared by both rank 1 and rank 2, and basically you have how many banks? 8 banks per rank, right? I think so, yeah. 8 banks per rank, and with 2 channels. Sorry, 2 ranks, 8 banks, and that's sort of how much utilization, how much bus utilization you will consume by refreshing every row in a single channel. You'll go through every single row in each rank on a single channel.
But don't you go through the different ranks at the same time as each other with the same command?
No, so
That's chips within a rank.
yeah, so a command only operates on one rank at a time, not multiple ranks. Yeah. So
can you go through
part A. So A is.
Figure out the number of rows. I got 2. And I know that.
You got 2? Okay. So we know that so for each row, it's retention time 64 milliseconds, right? So that means if you think about a 64 milliseconds window, you will have to refresh every single row. I think that's important. Does that make sense? Yeah. So basically, let's assume you have n rows. Within this 64 milliseconds, you will issue n commands, right? Okay. So in this case, the number of rows is r. Each refresh latency, how much is it? 40 nanoseconds. Yeah. So 40 nanoseconds over 64 milliseconds. Right.
And that's supposed to be like 0.02048.
So should we work on the math now? Okay. So basically R times 40 nanoseconds, 10 to the negative 9. I think some of you got the unit run for milliseconds. It's actually 10 to the negative 3, not 10 to the negative 6. A lot of people put down 10 to the negative 6 for some reasons. Okay, so R times 40 over 64 times 10 to the negative 6, right? And so 40R 64 10 to the negative 6 equals to 2 times 2048 times 10 to the negative 3. Yeah.
Shouldn't that be -5? Since it's a percentage.
Oh, you're right. You're completely right. Yeah, so it's 0.002048. No, wait. 0.2048, right? No, it's actually 10 to the negative 2. 2 point. I guess here, yeah. So 2, 1, 2, 3, 4, 5. Yep, 10 to the negative 5. Exactly. So do you want to continue working on it? But if you solve the equations, it should come down to whatever answer we have. 2 to the 15? Yeah. But do you agree with the equations? I think if you work it out, it should be 2 to the 15. Yeah. So did you have the equation correctly, or you?
I don't have my test right here.
Oh, okay. Yeah. Yeah. Okay. Is there anything?
There's a part asking like command bus hitting 100%.
Yeah.
Like something like for that. Do you just use the result from B and like use 100 divided by that times number of rows?
100 divided by number of rows. So what do you mean by 100 divided by rows?
So the answer was like 80,000.
Uh-huh. Yeah.
How'd you get 80,000?
Okay. So basically, let me see. Only change the number of rows, find the maximum number of rows per bank. Okay. So basically, when we'll basically take, I guess, the part B equation, right? So number of rows times 5 nanoseconds times 2 ranks, 8 banks over 64 equals to 1.
Okay, so what if you got B wrong
Did you show your work? If you show your work, I think we gave you partial credits. No? Okay. I think it's, yeah, I didn't realize. It basically depends on your answer from B. If your B is wrong, you cannot get D right.
B, like, I just missed the 2, like, it says 2 ranks or something.
Right.
I missed the 2, so I got 4 point something.
I see.
Instead of 2, so like,
Yeah, so you can submit for regrade
okay.
as long as you show your work. You have to show your work, though. If you don't show your work, we cannot give you any partial credits. Yeah. Okay, and everyone got E correctly, kind of? Asking how we can basically reduce the utilization without changing the refresh rate. Okay. Okay. So I guess Professor Mutlu already said that. I guess before that, do we have any other questions with the refresh? No, we're all good? Okay. So the next part is the virtual memory. So as you know, this won't be on your final exam. And this won't. Yeah, Professor Mutlu said it. This won't be on the final exam.
But he also said if you got, like, most people got it wrong, there's a high
Yeah,
chance.
so this is exclusive. Don't worry about this. Yeah. Yeah.
Will something could something very similar be on?
It won't be this long because this question, I don't think you want to go through it. It's
Please go through it. Please go through it.
really.
Please go through it.
It took us more than 1
That's the
hour
only
to solve that question.
Actually, it actually took us about 42 minutes to an hour to solve it.
Can it be taken off before the exam?
Yeah. So just to be honest, that's how long we took to. That's how long we took to solve the question. I don't think we want to go through it now.
I just have one question.
Okay, one question. Yeah.
Yeah.
So we can answer a specific part of it. Yeah.
Why is not, wait, so like it could be 300 or 3C0, right? And the answer was 300? Is that right? Or 3?
Which one?
Why is it not the other?
Which one?
So the answer for B, second part?
B. 3C0.
Okay, yeah. Why is it not 300?
Yeah, I got 3-0.
That is.
We have to work backward to find out what you meant by 300. I don't think.
Because, like,
I think I need to work backward
the
completely.
tag, and
Uh-huh.
there are 2 blocks as possible, the possible page directory based address, right?
Mhm.
So one is 3C0 and one is 300, and one maps to like 0A0C0A07 or something.
Okay.
So I thought that one was the base address.
Okay.
But it's not. Why is it not?
If I recall, it's the LIU bit. The LIU.
Oh, God.
LIU.
LIU bit.
Which bit?
RU bit.
That tells you something?
Yeah, it could be. So the one that was accessed first might
Yeah.
be the first level.
No, but there are 2 ways, right? So you access the directory and then you access the table.
Yeah.
Both of them will be in the
Yeah,
same
but
cache.
because it tells you which one was accessed second. So the one that was accessed second
What?
is the second level.
That was your reaction. What? Seriously? Where's the LRU bit?
In the table.
Oh.
Okay, you guys are cheap.
Yeah, but the VM question on the final exam won't be like this. We promised. Yeah. Professor Mutlu already promised, so we'll stick with that.
So he's got like two bases to, is that also a complicated?
Yeah, so basically, if you look at the answer in part C, it should basically help you walk through it. Okay, so I'll go to the high-level way to solve this question. Okay, so one thing is to know that you want to see that there's an address 0x3184, right? So by decoding that, you'll figure out where in the cache that instruction is. So I think it's this one right here, if I remember vaguely. It should be here. And basically, you have the tag bits, right? Yeah. So the next step will be finding the PTE, page table entries, for this particular instruction. So the PTE stores the PFN, for physical frame number. And you can figure out the physical frame numbers from this address here. Then that's how you sort of find the PTE entries. Then from PTE entries, you want to decode the address of the PTE entries, so you need the tag bits. You'll take out the tag bits from the sets. Basically, I think it's this one right here. Basically, take out the tag bits from the address so that you can reconstruct a physical address. And you also know the physical frame numbers of the PTE. Using a physical frame number, then you can find the PDE entries. And from that, the PDE entries, you find the address again and work backward. So it's a complete reverse engineering, yeah. So that's sort of a high-level way of solving this question. Yeah. Okay. So any other specific questions about exam 2? Exam 1, okay. What about exam 1? Caching question. Oh, yeah, that one. That was a tricky one, kind of. Yeah. So you want to go over it? Is that what? Okay. Sure, we can go over it. Sure. Yeah, that's fine. Oh. Okay. All right. So in this questions, you're trying to solve the block size of the cache, right? All right. So let me see. 16. So we give you several information. It's 16-bit addresses, three-way set associative true RU replacement policies, and the tag store is 264 bits of storage. Yep.
I'm really curious about how that hint is useful, because I solved this problem.
Mm-hmm.
The hint, I didn't see it. I think I'm gonna do it.
Okay, yeah. We'll go through it. Okay. So let's start from the beginning. In total, you have 16 bits, right? So what does that tell you? So basically, if you break down the address of 16 bits, you have the tag bits, the index bits, and the block bits, the block offset bits, right? Okay. So the next piece of information is let's first find the number of tag bits. Okay. I think that would be much easier, given that we give you the size of tag storage. Okay. So in the tag storage, what do you need? You need the RU bits, valid bits, and dirty bits, right? For each block. All right. So let's first figure out RU bits. So in this case, we give you three-way associativity cache and true RU. And remember your favorite equation, the factorial? Yeah. So this is the number of RU bits you need, right? Yeah, 3 factorials. Oh, I didn't write the. Sorry. Yeah. So basically it's 3, right? Per block. Okay. Per set, yeah. So basically each set you have 3 bits. And next, let's figure out what else do we need. We need the valid bit, which is 1, let's just say per set, 1 bit per block. Dirty is 1 bit per block as well, right? Okay. So next we need to figure out number of sets, which we do not know at this moment, correct? And here we just assume we have n bits for the sets. So that means in total we have 2 to the n sets, correct? Just assuming n equals to the number of bits we use for selecting sets. And what do we need next? Number of, okay, so we actually need, in order to figure out a tag storage, we need to figure out how many blocks we have. So with 2 to the n sets, let's say number of blocks. With 2 to the n times 3, right? That's the total number of blocks inside the cache. Okay, so now my tag storage would be, how many bits? So first is the RU bits. So we have 3 bits per set, 2 to the n sets, right? Next is we have, what else? We have 1 bit valid, 1 bit dirty. And so what do we need? So we need this. This is number of blocks. And this is valid plus dirty. This is your tag bits. Correct? Everything so far? Yeah, so now we need to solve this ugly equation. And that's really where the hint comes from. Okay, so if we basically simplify this equation, let's see what we can do. 3 times 2 to the n plus 3 times 2 to the n times 2 times plus 2. Okay, so this becomes 2 to the n, right? T plus 2. Correct? Correct? Everything so good? Okay, so this equals to 2 to the 8 plus 2 to the 3. Okay? Okay, so next thing you need to figure out is 2 to the n, 9 plus 3t. Let's say take out 2 to the 3, 2 to the 5 plus 1. Okay? Does that kind of ring a bell? You kind of know how to solve it now? No? Okay, so basically, so 9 plus 3t equals to 33, right? And n equals to 3. Okay. Does that make sense? T equals 8. Huh? Oh yeah, sorry.
So why couldn't n be 2, for example?
N equals to 2.
And then you just get 2 to the 6 plus 2.
Okay. N equals 2. Can you solve it with n equals to 2? So okay, let's try it. N equals to 2. So 2 times 2 plus 3 plus Okay. So basically 2 times 2, 66. So 9 plus 6. T equals to, which is,
Over 16.
yeah, exactly. Okay. That's where the hint comes from. Yeah. And I guess the final answer, we're not even done yet, to be honest. So basically, we need to find the block size. Okay. So block size here is, the block bits we have is 5. So it's 32. Yep. So that's how the hemp was super helpful, right? Yeah. We're able to get to this step at least? Oh, okay. Yeah. Yeah, okay. So I think it looks correct. Okay.
Can you go over the branch prediction question?
Branch prediction question. Okay, we'll have Rachada go over it. That's his favorite. He made up that question. So I think he can explain it better than I do. I can see the anger from him toward you.
I can see that too.
It's right here. I'll scroll through. Yeah, I don't know if you need it.
Yeah, I have a blank.
Oh, you can work from it here.
Oh, okay, cool. All right, so problem A. Can I zoom out a little bit? So problem A is after 10 iterations, you observe that the branch predictor is always right. What it means that if you look at this particular loop, whatever the value x is, and also regardless of what initially when you goes into that loop and hit that if-else statement, it's predict correctly. And if you look at the problem, GHR start as strongly not taken, so you have GHR as 0, and all the PHTE is strongly taken, is all ones. The only way you can have like always predict correctly is you have to always take it. Otherwise, you update these entry into toward not taken, and then you predict taken, but what happened? Actual branch is not taken. So what that means is that you always have to take whenever you have the branch instruction, and the only case that can happen is if that if is always taken, because if that has any one not taken branch in there, that first not taken, you mispredict. You always mispredict, regardless of what, because of the initial value be PHTE. So the only case that you always taken in that branch is it's modulo 1. So in this question, it's x equals 1. All right. So this, most people actually got the answer correctly. Do you want me to go over that as well, like the prediction accuracy?
No, I wanted to go over part C.
Yeah, so that's what I think we should go over. Part C is a little bit more tricky, which is if you run the code until you exit the loop and you see this final state of your branch predictor, and so in this case, what can you tell about the value of x and n? So if you realize if for that code over there, for any value that of x that's not 1, and if it's 1, it's also impossible because the final state would be everything in the PHT table will be all 1, 1. So you can eliminate x equal 1 from this question. If x is not 1, the pattern becomes so it will be taken. Right? You go into the loop, and suppose x is some value is not 1. It's going to be not taken, and go back to the loop again. It's going to be taken. Going back, that'll be not taken for a while until the index modulo x is 0. That becomes taken. So at that point, you have the pattern of 3 takens. Oops. Yeah. So eventually, at some point in time, you have 3 takens because you go into that loop, followed by taken, not taken, taken, not taken, taken, not taken, depending on the value of x. So if you realize there's a pattern that way, taken, not taken, taken, not taken, blah, 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 and then followed by taken, not taken, 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 not taken, taken, not taken, on repeat. Right, and now you should go back to the value of PHTE. Actually, let me just zoom out here. Right. Value of PHTE. When you exit the loop, one thing that happened is the loop, instead of taken, it becomes not taken, right? So the GHR is the last one. The last bit become not taken. And then if you look at this particular pattern over here, you see that the not taken, if you go into that if you update the PHT entry because it's taken before it exits the loop, and you see that the not taken entry over here, not taken, taken, still have the old value, which means that the iteration right before you exit the loop, you're not taken into that if. Because if you have the taken pattern there, that value should be 0 and 1. Do you understand what I meant? If you look at NT, right? If the value of GHR becomes NT, there can be 2 choices. The next branch you get you are evaluating can be not taken, which means that you're not taking into that if statement, or it can be taken, which is x equals n. But if you look at the final state of your PHTE over here, not taken is 0, 0, which means that before you exit the loop, you're not going to that if statement. So one thing you can tell is the last iteration, you're not going to that if, which means that x x n n mod x is not 1, which means this is just a condition that ensure that right before you exit the loop, you're not going to that if. And lastly, there's another possibility that you can have this nt become 0, 0 as well, because you can never actually go into that if ever. So another condition would be if x is greater than n, you never go to that if. So most of you guys actually got one of the two conditions. I think no one got both of them. Actually, it's greater or equal. Yeah, greater or equal, because if it's equal, you exit the loop right before. Yeah.
Well, if x is greater than n, then n mod x is not equal to 1, right?
Yeah, but in that case, it doesn't matter because you never go into the loop. So that's why you have to add that another condition as there, so to make sure you cover all the cases. Yeah. Because if x is greater than n, no matter what value of x, and regardless of how this results, you never go into that if statement, and you have to not taken on repeat, and you have the end result to be that pattern. Yeah. All right. Are there other questions on the Jira problem?
If you have time, can you go over the VLIW question?
Yeah, sure. Do you want to go through that, or let me read it first? Because there was. Right, so I guess we can skip that part. It's pretty chill. All right, for here.
Actually, yeah, could you explain the motivation of VLIW?
Yeah, sure. So for VLIW, one of the key benefits is you can issue multiple instructions in one cycle, right? And if you can assume that the compiler or the software layers can somehow schedule independent instructions and put that into the VLIW instructions, then you can actually keep issuing multiple instructions for every cycle. So that's the key motivation behind VLIW. Right. So do you want me to go over the first part? Because I think the tricky part is it comes later. Huh? Okay, sure. Yeah. For the first part here, actually let me be careful about the question. Wait, where's my screen? Right. I'm gonna keep this here so that you have the specification up there. So there are 3 fully pipelined ALUs, memory units, and also floating point. And they have different latencies. And if you look at the C code, which is shown over there are dependencies that happens across instructions. And for the first part, you have to figure out how you would schedule different VLIW instructions based on that code over there to make sure that you don't have like dependency or rest condition. So let's look at the code and see what we can fill in from that assembly code into the different instructions. The first one, and you have 3 units: ALU, floating point, and memory unit, right? So if you look at ALU, the first thing you can put in is you have add, right? So this is the first ALU instruction. So you have add I. But actually, this. Wait. This is dependent. Wait, what? Why does the solution do this? Actually. Here, let's go through the assembly code line by line first. You have a load and store. So first, you have the load go to memory unit. So you have to LG F1 0 into R1. And on the floating point, if you look at this, every floating point instruction dependent on F1, so you cannot schedule anything. So this becomes no ops. The next instruction is the load. So you have load F2 0 R1. Next instruction is multiply. So over here you cannot schedule anything to the FPU still because you're still waiting for that load.
Where the latencies are taken care by the compiler itself. I mean, the compiler knows that the result of this node is going to be available after 2 seconds.
It has to figure out the dependency, and so that when you schedule the actual instruction, so the bit pattern of your opcode, when you fire it off to the hardware, you won't see this same assembly code. It will be like vector VLIW instructions being handled by the compiler, and the compiler has to figure out dependency and also optimize how would you schedule these instructions, which they have different algorithms. You can do more greedily, build a graph based on the latency, and then try to like parallelize everything. That's one way you can do it, and there are multiple ways you can do it. Yeah. So the next floating point multiplied, you can fit it here, F multiply, because now you resolve the load based on the specification over there. So you can do F multiply F1, F1, F1 here. For the next instruction, F add, because the latency of the floating point units is 3 cycles, so you cannot really fill in anything here. You have to put in no ops for these 2 cycles. And the reason you couldn't do the load, I think it's multi-port, if I recall. Floating memory units 2 cycle latency.
So you wouldn't be able to do that, would you?
Hmm?
I don't see where it says it's multi-port.
Yeah, I'm trying to search for that. So.
It's pipeline. Oh, it's pipeline. Okay.
Where does it say pipeline?
Is it? I think it's the first bullet.
Oh yeah, it's fully pipeline, yeah.
Then the FPU would also be fully pipeline, right?
No, it's dependent on F1.
Okay.
Yeah.
Sure.
So do you do F add over here? F1, F1, and F2. Next instruction is add I, R3, R3, 4. And you should be able to fill it in here. Yeah, R3, 3, 4. And then the next one is a store. And that stores need R3. Wait. If you look at the solution, the thing is add I, R3, R3, 4 happens at the end. I'm trying to figure out why that's happening. Anyone has any idea what happened here?
That could be in the throat center as well, right? But it doesn't matter, I guess.
No, it would matter because the store based on R3, so it has to wait until that results come out.
What's the question?
Store is also waiting for F1, so that comes out in the last sequence.
Okay, yeah, that's true. Right. So the add I over here doesn't matter. And then you have, what else? You have over here R1. And it waits for R1. Where's R1? load. So you can do the add it over here. R1, R14. And you have another add I. Oh, I missed the store. But let's do in the add I first. So R2, R2, 4. And then you have a store that waits for F1. And F1 is the floating point add over here. So we take 2 more cycles before you can do the store. Store F1, -4, 3, right? And the rest is no ops. No ops. So if you look at this table and you do the number of cycles here, which is 9 PL or IW instructions, and number of operations, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So you get 9 over 9 equals 1.
Is it explicitly, it is required to send NOPs exclusively even if there's not even a single instruction in the entire?
Yeah, because you have to tell the functional unit, so the decoder on what to do with the functional units. So the easiest way is send knobs, so that I guess you can set power. I mean, so that you don't do some other weird instruction, because I mean, potentially it's don't care, but you have to make sure it doesn't do anything. All right, for the next part. So you unroll the loop once. Actually, let me go to the code from this screen. So you do the loop unrolling once. If you unroll the loop over there, what happens is instead of the combination of 2 loads, what you have here is with the 2 loops you have 4 loads. So you can do load, 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 and this go to F1, F3, because that's the second iteration of the loop, and then F2 and F4. And that's 1. And that's 2, 2. And now when you do the floating point here, units over there, the first floating point, the multiplied on that, where's the code? Over there, the F multiplied depends on F1, so you have to do it. You have to put knobs over here, and then you do the F multiply, F1, 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 and then you can follow through with the second multiplied, which would operate on F3, the second unroll version of the unroll loop. F3, F3, F3. And then, what's the next instruction? Is the add. So the add, you can actually do it here. You can do add I. Because you do loop unrolling, you do add I R1, R1, and put 8 here to do it twice. And then no ops.
You could do that in the first cycle as well, right? Or, oh no, okay, I got it.
Oh, okay. So it's actually 2 loops. So the same goes here to add. What's the next? Oh, the next instruction is store. And you have to look at how store is dependent on this. Where's fadd? The earlier fadd over here, the 4th line of your instruction. And I haven't filled that in yet, but if you look at how this goes, you have no opt here. And because you did the loop unrolling, the first F1 over here will be ready by this cycle. So you can do the F add. F1, F1, F2 over here. And the next would be F add. F3, F3, F4. Right, so once you have that add, you have to wait 3 more cycles. So this 1, 2, 3, and then this is where this is where you can do the store. So you can do the first store over here, F1 0 3, and the second store, which is the unrolled version over here, F3 -4 3, and then no ops here because that's all we have to do. And I don't think there are any more load and store, so these are all no ops. And then we have to take care of the rest of the ALU instruction after that store. So you have add I. I think over here is fine. Add I for R2, and then for R3, you have to wait for this. So you can do it toward the end. Add I. And then you have branch over here. So then these are no ops. So you see you have 10 cycles, 10 VLIW instructions, but you actually did 14 operations because it's less than like 9 multiplied by 2 because you combine 2 ALU instructions together, and that's 14 over 10. And here's the tricky part. Actually, I will call it the part that takes longer to do because now you do loop unrolling multiple times.
Question.
Yeah.
Why can't I just unroll the loop completely?
You mean keep unrolling until infinity?
Yep.
Yeah. So that's why I said it actually take a long time to solve this question because after you unroll more than 5 times, if I recall, you realize actually you get fewer throughput because you have the bottleneck. There's a bottleneck that exists.
But then I think the overall cycle count is less because if I unroll it
Why would it be less?
If I unroll it completely, I don't have anything to do with the loops. So my instructions is less, but the total cycle might be less.
So there's a possibility, but at some point you realize that one of the functional units or one of the memory units would become your bottleneck because you have to wait for that anyway. So you cannot always do the full pipelining of these loads from multiple loops iteration together. And at some point, I think for this case, if you do it 5 times, that's the best in terms of operation per VLIW instructions that you can get out of for this question. Yeah.
But if I unroll it completely, the performance in ops per cycle is down because I don't have extra operations for the loop, for the iterations. I only have one.
You just have no ops, a bunch of no ops.
Yeah, the memory is still the bottleneck, but I think the total cycle count is less. I only have to wait for the memory, and that's it. I don't have to wait for the memory.
Have you actually did unrolling?
Yep, that's what I did. That's what I did.
Okay. Can you give me a look? Can you give me a look? Yeah. So you might actually miss some dependency over there. So if you did it by hand for each iteration, you see that after 5, it actually decrease the number that you get in terms of operation per VLIW instruction.
Because I don't have many overall operations. That's the point.
Then why can you assume that you can always schedule instruction that way? Like why can you assume? Because what you did is you assume that you have some bottleneck, right? And you can schedule instruction that way. But there are multiple dependency between each instructions. It's not just each each unit has its own bottleneck too. So you can always pipeline those. But other ALU, like say for example ALU, the R3 has to wait for the load and store.
Sorry, can I interrupt a little bit?
Yeah.
I have a meeting that I have to run to right now, but Rachada will be here
Yeah,
until
I'll cover the rest.
probably 20 or 30, and
Yeah.
however long
Yeah,
you guys
how
want
long
it to be. But we'll have office hours on Monday. So if you have more questions, either post on Piazza or stop by our office hours.
Do you guys have midterm 2 right now, or?
So if you haven't picked up your midterm 2, they're in the course hub.
Yeah.
So right across from the room.
There's no recitation today?
There is recitation today. So there's going to be recitations and office hours today. Yeah.
Do we need to get checked off on Lab 7?
Yes. That'll be great.
I'll be here.
So you can check off after the class. It's very quick, yeah. We just ask you several questions regarding how you did Lab 7. But it shouldn't take you more than 2 minutes. Yeah. Okay. I'll see you guys later. Any more questions? What?
Where's recitation?
Recitation? It's in the code.
Okay.
Yeah. Okay. See you guys later.
Okay. So let me put it this way: if you think you unroll the loop and can write instruction, you can write a script that do that unrolling and show it to me. I'll give you this back. Because we are pretty convinced it's not that's not the case.
Okay, I'll try.
Yeah. All right. You guys have any other questions?
Yeah, in the porphyry part.
Yep. Midterm one.
Can I ask a brief question about this part?
Yeah, sure.
So why do you measure an ops per cycle when the number of ops might change?
Yeah, so it's a little bit. So we want to be careful how you count the ops because we don't want you to count no ops.
Yeah.
That and also, so eventually you want to ask you the question of like what's the useful unit of operations per cycle, and in the end it's like we want to make sure be careful how we define things so that you don't count either. You don't put like no ops everywhere, so you have like really long, really good throughput, or you count instruction in a different way or count cycle in a different way. So it's more like a semantic kind of thing.
Okay, but like even though one set of code one program might have higher ops per cycle, it might still have lower like performance, right?
It can, because so now that's another different kind of discussion on how you measure performance. Because in the end, what you care about is execution time.
Yeah.
But in architecture, we actually evaluate how things perform. You don't always get the luxury of getting the execution time because we are actually running big applications. So when we do this evaluation, we can look at throughput, how many instructions you can retire. So that ops per cycle would be, if you have more ops per cycle, it might be, your processor might have more performance, might perform better. But if you optimize it differently, one op, for example, GPU, one op in the GPU might not be the same as one operation in a sys processor, because one instruction over there might be like doing a modulo or something, or like test a prime, which is many instructions. So in that case, ideally we want execution time. So if you actually read a bunch of papers, there are actually a few papers discussing how would we pick this metric to make sure it kind of resemble the execution time. And there are different ways you can reason about the workload, and also like whether it's a multi-threaded, whether it's a GPU, whether it's a multi-core CPU. So yeah, to answer your question, it's true that ops per cycle doesn't really mean it performs better. Yeah. All right. So which potpourri?
Yeah. So Part D?
Part D of midterm one?
Yeah.
Okay. So here's the question.
So how do you exactly go about calculating the number of branch linear plots you require and out of order execution?
Oh, I think it's a trick question because you don't know how you're going to schedule this instruction, so you don't know.
Yeah, okay.
Yeah.
Okay.
So that's a red herring. It's a trick question.